Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Aldana Grichener with us today. I kind of missed that, but it was close. How you doing, Aldana?
Great. How are you? Thank you
I'm
so much
doing
for having me here.
well. Thank you for agreeing to talk about your very awesome article, which we'll get to here in a second or so. So it is September 17th of 2025 as we record this. And Aldana, what is your current geolocation?
So right now I'm in Tucson, Arizona.
It's about 90 miles, 100 miles from me.
Yeah.
So is it a little cloudy today?
Yeah, but at least we are not at the triple digits now.
Maybe. Maybe. There's certainly been Octobers where we have definitely hit the triple digits. So yeah, but I think we're out of the big heat, right? I think we're out of the 115. So that's for sure. So yeah, very good. Um, and Aldana, what's your position there in Tucson?
So I'm a postdoc at the University of Arizona. It's my second year now.
Oh, very nice. Congratulations. Awesome.
Thank you.
Yeah. Let's see. And Aldana, what do you like to do for research?
So I usually work at the intersection between nuclear astrophysics and stellar evolution. Like I enjoy having it like both of these ways. And basically I study massive binaries and how they affect high energy astrophysical phenomena that has to do with nuclear astrophysics.
Very cool. Very cool. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Nuclear neural networks emulating late burning stages in core collapse supernova progenitors. And Aldana, take us away.
Yeah, so this was actually a project that started when I was at the Kavli Summer Program at Max Planck Institute that was organized by Selma Deming and Stephen Justin that are both here in the list of co-authors.
Uh-huh.
And it was actually kind of outside of my field of expertise at the moment because I've never done something with machine learning, but it was an awesome plan where I met all of these nice people that are appear here in the author list, like Mathieu Renzo, which was my close collaborator on this project, Wolfgang Kenzerhoff, and all the rest of the people on the list. And it kind of started like as an intensive 2 month project that then was a little less intensive as everyone gets scattered into their original geolocations.
Yep.
But I'm really happy that we managed to get this publication out at the end.
Very cool. Great shout out. Great shout out. Okay, let's get into it.
Yeah, so what we do in this paper is basically try to use neural networks, meaning surrogate models that were trained by neural networks, in order to replace the differential equation solvers of nucleosynthesis in stellar evolution codes.
Mhm.
So basically, what happens in stellar evolution codes is that when we go into late burning stages of massive stars, that are stars that are going to end up exploding as supernovae, it's really, really hard to simulate them. And because it's hard to simulate them, then at the end, it's hard to have enough of these progenitors to give them to 3D hydrosimulations in order to study the explosion.
Okay.
So, and the reason why it's so hard to simulate them is due to actually the stiffness of the differential equations that are in charge of nucleosynthesis. So if you scroll down to the first equation that
Sure.
we have,
Let's see. Let's go to equation one.
equation one, so how difficult it is to try and actually solve these and model these kind of late burning stages in massive stars is because of these equations that you can see here. This is the equation that takes charge of nucleosynthesis in stars, follows the evolution of an isotope in time. But in the stage of silicon core burning, which is the stage right before the supernova explosion, then we have hundreds of these equations that are fully coupled.
Yes.
Because they're fully coupled, like they get really, really stiff. And every time we add another equation to these hundreds of coupled equations, we are not only, when we're adding one isotope, we are not only adding one more equation, but we are also adding a term for its destruction and formation in an equation that already exists.
Okay.
So basically, what happens here is that we make everything even more coupled, And this is also coupled with the stellar equation
Uh-huh.
through the nuclear energy generation. So what ends up happening when we try to model these things is that instead of being able to get to the stage right before the collapse, stop the simulation there and give this model to a 3D simulation where you can study the explosion, basically everything starts getting stuck because you can't find an acceptable solution for this equation. So we try with smaller and smaller time steps all
Yes,
the time.
I'm with
And you start with the smaller and smaller time steps, then at the end you get to time step for about 10 to the minus 22nd when you know, okay, silicon core burning occurs during these kind of days time scale. So with 10 to the minus 22nd, the simulation is not going to continue and everything is going to crash.
cool.
And this is actually a problem because we know that we would need these physically reliable supernova progenitors in order to explore supernova explosion and understand all of the things that have to do with massive star evolution and binary evolution, because it also determines which stars are going to form neutron stars, which stars are going to form black holes, whether binary systems that massive stars really, really like being in multiple systems are going to survive each of these supernova explosion, what this will tell us about gravitational wave progenitors. So it really has a lot of impact in a field of massive stars.
Cool. I'm with you. Hmm. Good.
And what is actually done now in a lot of stellar evolution codes in order to solve this problem, being able to actually generate these models for supernova explosion is instead of using all of the isotopes that you know they're supposed to exist in these nuclear reaction networks, we kind of have these really small networks, about 20 isotopes and so,
Okay.
that can reproduce some of the properties prior to the explosion. But if you scroll actually to the figure when you have the pie charts, I
My
think it's
charts. Figure
yeah,
two, I think. Three. Let's go to figure three.
yeah.
Figure four.
I think it's figure five
Hi, we'll get there. No, figure
at
six.
some point,
Six.
or six, yeah.
Okay.
Yeah, so when you go to this figure, you can actually see that when you're trying to use these small nuclear reaction networks, then and compare the result. So if the small nuclear reaction networks on the right and compare the result to the result of the large nuclear reaction network that you have on the left,
Hmm.
you're not quite getting the same compositions and the same quantities. So there are small networks that can be useful for several evolutionary stages. When it comes to really before the collapse, you might still have some room for improvement in order to generate more physically reliable core-crab supernova progenitors.
Okay.
And the way that we tried to address this in this project is by using these machine learning methods.
Hmm.
So if you can scroll up to figure two,
Let's go to figure two, which is going to be our neural network. Yes. Figure
yeah.
two.
So basically what we do is we designed neural networks in order to kind of replace the differential equation solvers in stellar evolution codes. And so you don't have to do the nucleosynthesis on the fly every time that you're running your code, but you're going to replace them with these surrogate models that give you fits to what the nucleosynthesis yields are going to be.
Okay.
So
Mm-hmm.
what these neural networks do is they take as input the temperature, density, and composition of a burning shell of a star, what we call like a zone in the more professional jargon.
Uh-huh.
And then what they try to predict is what would be the typical composition and energy generation and energy that is lost by nuclear neutrinos after a particular time step.
Yep.
And in order to actually train the neural networks to predict these things well enough, what we did is we generated these really large data set of about 10 to the 6 nuclear outputs.
Okay.
And when we generate these data sets for time steps that are small enough so nucleosynthesis can be decoupled from stellar evolution, and
Okay.
then we fed all of these data sets to the neural network. So when they see something that is within the regime of the training, then it could actually tell us what the results are going to be without actually having to solve the equations.
Nice. Very nice. Okay.
Now, yeah. Now, in order to try and understand what are the regimes of interest, you can scroll back to figure one.
Figure one. Let's zoom in
And
a little bit.
basically, what we did there is took these models that are run with large nuclear reaction networks that take months in order to make them converge. And from these models that are on the curves that you can see for the temperature on the upper panel, the density in the middle panel, we actually tried at the beginning to actually make these neural networks trained only on these curves and more curves that were varied around the central isotopes.
Okay.
But then what happened is that the neural networks weren't really able to do a lot of generalization, meaning they were working, giving good results really, really well to things that were really close to these initial conditions. But when you went a bit upwards or a bit downwards, then they gave completely nonsense results.
Okay.
So in order to overcome this challenge, what we did is said, okay, let's take these curves for the upper and lower bounds of
Okay.
our training sets. And then what we did is said, okay, now we are going to do a grid of different results. We are going to take different points from the brown regions in the figures,
Got it.
and saying, even if we're not on this curve, we are still going to train the neural networks
Okay.
on these grids. And
Okay.
even though we are getting some results that are not never going to be in real stars, we're still enabling the neural networks to do this generalization. This actually worked quite well.
Cool. Very cool. Okay. I'm with
Then
you.
to actually understand like what are the time steps on which we want to train the neural networks, we looked at the typical time steps that these MESA models take during the simulations.
Huh?
And we went a bit below this time step, so we can also give the code a possibility to take smaller time step and do things that might be more relevant for hydrodynamical simulations.
For example. Okay. Cool. I'm with you.
Yeah. So basically, what we did is after we had these models, we generated 10 to the 6 training steps that we fed to the neural network, trained the neural network on these models, and then tested the results of these neural networks on data that it didn't see during the training.
Okay.
So this can bring us to figure 3,
Okay. Figure one.
where we show the results. If you want more details on the actual architecture of the network, you can go to section 2, but I'm not going to go more into this during this interview.
Okay.
Okay, so what you can see here is the error that the neural network is giving compared to the large nuclear reaction network that we are taking as the absolute truth.
Okay.
Now, you need to remember that there are a lot of uncertainties about nuclear reaction rates and all of these kind of things, but the neural network can't really know about it. All it can do is try to predict the thing that we trained it on. So
Yes.
it is never going to do better than the large networks.
Yes.
What is going to happen is that like a 100% success will be if it gives you the exact same result as the large networks that contain 80 or 151 isotopes. So like the upper panel is for the case of 80 isotopes and the
Okay.
lower panel is for the case of 151 isotopes.
Okay. I'm with you.
So we can see that when we're talking about compositions, these errors are still very large when we're going into the average case. But
Yeah.
if we go back to figure 6, when we had the pie charts of the composition,
Yeah. The selection
then they
error.
show how we actually tracked stellar composition with an average error in other values of the star. So
Okay.
remember that we started this by saying on the right we have what the small networks give us for the same initial condition as the large network.
Uh-huh.
Now we can see in the middle what the nuclear neural network are going to give us.
Uh-huh.
So we
Okay.
see that while we still have room for improvement because we're not getting the exact abundances correctly in these cases, we
Better.
still see that we are getting the main features and the main burning products.
Yes.
And it's performing better than the small network when talking about one time step. Now, if we go back up, we also try to understand the typical errors. Yeah, so going back to figure 4 maybe at this time.
Figure four. Okay. So these are the errors. We're still kind of large in spots. And figure
Yeah.
four. Okay. Here we're going to do some comparisons. I'm going to zoom out a little bit. There we go.
Yeah, so basically here we are looking at some physical quantities that are going to be relevant for the explosion of stars. I think like the most prominent answer is the electron fraction,
Uh-huh.
which is basically how many electrons we have per baryons in the flow.
Yes.
And the reason it's because it is so important is because it goes in a quadratic term in the effective Chandrasekhar mass, which would be the maximum mass of the iron core that is collapsing that can still sustain itself due to electron degeneracy pressure. Or
Okay.
looking at it at a more simple way, basically what ends up blowing up the star is the fact that electrons merge with protons and form neutrons, and there are proton-neutron stars formed. So getting the amount of electrons right is really important to understand whether a star is going to explode and when it is going to explode.
Cool.
And here we can see in this figure, when we are taking different time steps on which the neural networks were trained that are logarithmically spaced between 10 to the minus 6 seconds and 10 to the 2 seconds,
Okay.
then we have the green crosses, which
Yes.
are the errors of the nuclear neural networks
Okay.
compared to the large networks. And we have the blue curve, which is the error of the
Oh,
large networks, the small networks compared to the large networks.
gotcha.
Meaning, what we're trying to do in this project is not like solve all the problems that are due with nucleosynthesis, just make something that would give us better results than the small networks.
Yes. Yeah.
So we can see here that indeed, like for the electron fraction
Hmm.
and for the average mass fraction and for the nuclear energy generation, we're getting better results with a couple of times than the case of the small networks, while for the neutrino energies, we still, for a large time step, we would need to improve our results, but for time steps that are relevant for silicon core burning, then I think we could be
Right.
fine in this respect.
Right. I
And
don't think anybody's
if
going to
you
be able
want,
to predict time steps.
yeah. So if we want to see this a bit more clearly, we can scroll to the next figure.
Okay, let's go back to normal size and we will go down
Yeah. So
four.
here we have like the exact same results with a different representation where what we're showing is the percentage of improvement
Okay.
of in these quantities when using nuclear neural networks compared to the small networks.
I'm with you. Hmm.
And this percentage of improvement, you can see that it varies whether the networks are trained on 80 isotopes or 151 isotopes, but it's basically in the regime, in most cases, between 3 to 8 times better.
Yes, definitely. Okay, good.
Yeah.
Nuke. E is actually pretty good, about the same, which would kind of make sense. Okay. Uh-huh. Good.
Yeah.
Cool. Very nice.
Yeah, so now when thinking about trying to implement these nuclear neural networks in stellar evolution code, then one thing that we are thinking is how much is it going to speed up the simulations.
Yes.
So if we go to the next figure,
Okay, let's zoom out. So we're on figure 5. Figure 6 we covered, so maybe figure 7.
yeah, so if we go to figure 7,
Uh-huh.
then we're trying to do a comparison between how much time it would take to do the tests with neural network trained model and produce compositions and energy terms
Okay.
compared to how much time it would take with the large nuclear reaction network that you can
Okay.
see. So the neural networks are the field circles and the large networks are the empty squares.
Yes, it's quite.
So we can see that depending on the nuclear reaction network, we have about 30 times faster when comparing the trying to run these nuclear neural networks
Cool.
on the data and trying to solve these accurately with the differential equation solvers.
Uh-huh.
And there's also something also that interesting that we're seeing that even when we are trying to actually use the neural network and compare the performance to the small networks that are already implemented, we still get some sort of speed up
Hmm.
between 1.5 to 4 times faster. So this is
Nice.
pretty reassuring in
Nice.
this sense. And also one thing that I think it's important to understand of this figure that this basically is going to be the minimal speed up. Because here we are only comparing apples to apples in the sense that we are comparing models that ended up converging, meaning running things only on nucleosynthesis data.
Yeah.
But in reality, the things that actually causes the computational bottleneck is going to be all the models that go to smaller and smaller and smaller time steps until they crash after, I don't know, 2 or 3 weeks or a month of running them, and hold the human time that is invested in trying to numerically stabilize these models to get them to push through silicon core burning and reach to the stages of core collapse. So all of this is not really represented in this plot. It only says like if we're taking like things that worked out,
Right.
how much faster it will work out.
Good. Fair enough.
Yeah.
Yes. Very,
But
very good.
yeah, but something that, so this is basically was a proof of concept of like introducing this new method
Uh,
of using this neural network framework that we developed in order to try and see if we can get more reliable core collapse supernova progenitors for 3D simulations. There are
uh-huh.
still some things that we need to take into consideration before actually implementing these in stellar evolution codes.
Okay.
Because the things that we are trying to do is basically, I think the most important thing would be that all the things that we showed here were showed for one time step.
Yes.
But stellar evolution codes are going to take a series of time steps.
Yep.
So, and what we need to try and understand is how the error of the neural networks are going to compound compared to the errors of the small networks.
Good question.
So we did do some minimal test about it when what we did is run the output of the neural networks on itself, meaning taking the output of one time step as the input of the following time step.
Yes.
And we saw that for the electron fraction, we're converging on an error that is twice as large than the error that I showed today, but still twice better than the error from the small nuclear reaction networks.
Sure.
But the thing is, this is not really what the stellar evolution code is going to do, because between time steps, we're going to have mixing and changing of the temperature, changing of the density.
Yes.
So actually understand how the error would compound, we would need to actually implement these in the stellar evolution code, run these alongside the accurate solvers, and make many more tests.
Right.
Another physical thing that would be important here is try to impose energy conservation, which is something that is not imposed by the code at this moment.
Yes.
So, because we are actually directly emulating these nucleosynthesis yields, we are directly emulating the energy, but we are not computing the energy from nucleosynthesis yields.
Right.
So I would think that we would need to actually to try and have many more time steps and have many more nuclear input data, like maybe vary the CPL alpha gamma reaction rate or other things that can do a different for stellar evolution explodability. But we're
Right.
basically showing this method that seems pretty promising in the
There you go.
sense of trying and getting these computations.
Uh-huh. Very cool. Very cool. And I should mention there are a couple of awesome appendices A, B, and C. You can check those out. There are three very nice figures in there. Check them out if you want. Very cool. That was awesome. Aldana, thank you so much for walking us through your very lovely article. Very cool.
Well, thank you for letting me this opportunity to present my article here.
Sure. Beautiful work. Beautiful work. Okay. Let's see. And you kind of touched on it a little bit there toward the end on some next steps that might happen. And I'm going to push on that a little bit and ask you to go a little bit further. And where do you think we go from here, given the current article and where we go? Is this, for example, is this a tool that people can download and play with currently? So is it open source? Do you imagine wrapping this up into some module that could be just plopped into some 3D GRMHD code to do the core collapse, or in the stellar evolution code or something along those lines? You also mentioned the possibility, I mean, there are uncertainties in the rates, and there are various reaction rate libraries, StarLib, for example, that will give you uncertainties on the reaction rates and how you incorporate all that. And yeah, just sort of next steps. Where do we go?
Yeah. So actually, I'm going to answer this question in stages. So regarding the open sources, so if you can pull out the article again, actually,
Okay, I shall do.
in the data availability section,
Uh,
I put a link to a guide that I created to actually have people have the opportunity of like play with this data for the things that they
there
want
we
to be
go.
able to do.
Done to do
So we have, I think it's in footnote 16.
Oh, very good. Here we go. Very nice.
Yeah, so here like I have these link to an actual interactive guide where I explain about these neural networks. And basically what I explain is how to create your own nuclear neural network. Because let's say that there are people that see this article and say, oh, like it is really interesting, but I'm not interested in silicon core burning,
Yeah.
but I'm actually interested in oxygen burning, or I'm
Okay.
interested in another evolutionary stage. So
Uh-huh.
they can go to this website and basically have the directions for how to generate data sets for training neural network, how to play with the architecture of the neural network,
Uh-huh.
and how to do a good test of this data. And
Nice.
actually, I already have some people that have been contacting me that they were trying to actually play around with these. And one
Good.
example was a group from UT Austin where they're trying to use this neural network for these chemical reaction rates in the ISM, which
Yes.
basically it's
Yes.
not nuclear, it's chemical, but we basically
It's
can use the same
diffeomorphic. Yeah.
technology.
It's diffeomorphic. Yep.
So it's interesting all the application these things can have, and everything is completely open source. Like I put all the data that I use to train the networks, all the scripts that I use to generate the plots in this graph. The only thing that I wasn't able to put is all like the extended data sets that amount to about 4 TB.
Right.
So no one is going to give me this amount of space.
No.
But if people are interested and want like other regimes or other time step, then if they have an hard drive and can or have a reasonable way of transferring the data, then I'm really happy to share.
Cool.
Yeah, but
Along those lines, another area that might be ripe for this would be, non-LTE, right? Where you're basically solving a bunch of rate equations for the different population levels, and it's the same question, it's the same process. Yeah. Hmm.
yeah, it's a really interesting process. Regarding implementing this in hydro simulations, so I'm in contact with the group of Fritz Rupke at HITS that are trying to see if maybe they can use this neural network not for doing this large nuclear reaction network, but actually to reduce the time it takes them to use small nuclear reaction network. So in hydro, even using like the small network, it really hits a lot of the computation time. So it is also a direction that we're looking at. I think
Yes.
that the natural next step is that we're in communication with the Mesa developers
Yeah.
and trying to build a framework to actually integrate these neural networks
Cool.
in SR evolution code and see
Uh-huh.
how far off we are from where we want to be and what we need to do to improve our model in order to actually get these working and running. And I think that there could be exciting implications because in cases where we actually can eliminate like the bottleneck from that comes from these nucleosynthesis in late stages. We could also have better prescriptions for exploitability in population synthesis, and there are all open avenue for these kind of things that we could do if we could kind of speed up stellar evolution instead of trying to glance over the stage because it's numerically unstable.
Or challenging to do. Uh,
Yeah.
so A, go Mesa devs. And B, if this works out really well, you could imagine this supplanting, because right now what people do is they will do the hydro and they will put in tracer particles. Why do they put in tracer particles? Because the burning is so expensive, right? But if you could do the burning, put it on par with, let's say, the equation of state or something like that, you could get away from doing tracers and incorporate the burning live in as you go. So yeah, there's a lot of very interesting applications of this. So very cool, very cool. Aldana, thank you so much for walking us through your very awesome article.
Thank you for having me.
Sure. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.
Bye.